Hey guys, in this particular video I'll be talking about elastic energy, and in order to derive all the equations used for elastic energy we need to know two things. First of all, we need to know that work, that is, the work done by a force acting on an object, is equal to the integral of the force, of that same force, dot dr. Another thing we need to be really familiar with is Hooke's law. And as a brief revision on Hooke's law, let's say we have a wall right here and we've got a spring that's initially unstretched and attached to an object. And let's say we were then to stretch the spring a little bit, say to the right, and leave our object, say, right here. Consequently, and this will satisfy your intuition, the spring will be trying to push the block to the left because you've displaced the block to the right. So in other words, the magnitude of the force acting on the block by the spring will be kx, but its vector direction will be in the opposite direction to its displacement. So we put a negative sign out here to indicate that it's actually in the opposite direction to the way you've moved it. And this is totally fine for a one-dimensional case. So this will be F due to the spring in the x direction only. But if we wanted a more generalized understanding of how to apply Hooke's law, we really need to invoke all three dimensions. And the easiest way to do that is using vector vector notation. So we can actually write in general that the force acting on an object by a spring is equal to, and it's a vector because it's got three dimensions, or just dimensions in general, will be equal to negative k times by r, where r is your displacement from your equilibrium. And to make this concept a little bit clearer, I've got a picture right here which might explain things a little bit better. Let's say that we've initially got a spring and it's unstretched, and this is a picture of that spring. And consequently, let's draw, and let me just do that, find a black pen. Cool. Let me just draw our axis right here. So I've chosen my axis to be at the midpoint of the ball, assuming that it's in equilibrium, right? So this will be x and this will be y, say, right? And let's say we were then to stretch the spring a little bit more, and I've got a picture of that too. So this is the spring now stretched a little bit. Consequently, we can say that our displacement vector will be from our equilibrium position, because that's where we placed our axis, to some arbitrary point which we've displaced it to. So this will be our displacement vector r. And we know, and let me write it down in white again, we know that r is just going to be equal to x, y, z in the most generalized sense. So in other words, we've displaced this ball from its equilibrium position a distance x in the x direction, a distance y in the y direction, and a distance z in the z direction, right? We can use everything we know here to try and work out what is the work done by the spring force alone. So in other words, there may be other forces acting on this ball, but we're only interested in the work done by the spring. And then we write down that work as the work done by our spring as W subscript spring. And that's going to be equal to the integral of our force, which we know is just going to be negative kr. So it's going to be negative, actually, let me just do it all out. I won't skip the intermediate step. That'll be negative k times x in the x direction, negative k times y in the y direction, and negative k times z in the z direction. And that's going to be dotted with your small displacement vector dr, which is just going to be dx in the x direction, dy in the y direction. Oh, let me make that a little bit clearer. Dy in the y direction, and dz in the z direction. Alright. Well, we've done this many times before. We've evaluated the dot product, and we know that that's just going to be equal to minus k, actually, let me write it all out. I don't want to skip any steps for you guys. That'll be minus k dx minus k, sorry, that's minus k x dx minus k x dx minus k y dy minus k z dz. Right, that's after doing the dot product of this, and notice that this is a scalar right here, which is something we'd really expect. Alright, well we can evaluate this quite easily now. We know that the integral expresses some distributive properties, so we can actually integrate each of these individual components. And I'm sure by now all of us are fairly familiar with integration, so I'm just going to skip that step and just write this as minus k times by the integral of x dx minus k times the integral of y dy minus k times the integral of z dz. And notice that the limits of integration will be from state 1, your position in state 1, to your position in state 2. So this will just be x1 to x2. These will be your limits of integration right here. Likewise, the limits of integration here will be from y1 to y2. And limits of integration here will be from z1 to z2. Not too much of a surprise. It basically says that if your ball is located at some arbitrary position x1, y1, z1, and then it goes to another arbitrary location x2, y2, z2, what is the work done? And it turns out that it's going to be equal to this beast right here. But maybe we can simplify this a little bit more. Well, doing the integration, we're going to get minus a half k times by delta x, x2 minus x1, plus delta y, or in other words, y2 minus y1, plus delta z, z2 minus z1. Alright, so here we've got a, sorry, that should be squared right here. All these terms should be squared. All of these terms should be squared. And they should be squared because if you'll recall from calculus that the integral of x dx is just going to be equal to x squared on 2 plus c. And of course the limits of integration get rid of that integrational constant. Alright, well let's see if we can simplify this a little bit more. And it turns out that we can by using something we call the magnitude of our vector. So recall that the magnitude of our displacement vector r is just going to be equal to the square root of x squared plus y squared plus z squared. And that's because our displacement vector r, as I've got up here, is just this. And we know from Pythagoras, you could just kind of imagine it in 3 dimensions, just calculating the length of this particular type of vector, and using Pythagoras you'll get this, but I'll do magnitudes in a separate video. So consequently, we can write this now as, and let me copy it for you, we can now write the displacement vector at position 1 is just going to be x1, the square root of x1 squared plus y1 squared plus z1 squared, and the displacement vector at position 2 is just going to be x2 squared plus y2 squared plus z2 squared. Consequently now, if we were to rearrange what's inside this bracket just here, we can rewrite that as minus a half times k times by x2 squared plus y2 squared plus z2 squared minus, I'm going to group them all, x1 squared plus y1 squared plus z2 squared, sorry, z1 squared. Alright, well what do we notice? How can we simplify this a little bit further? Notice that this right here, this term just here, is just the magnitude of our displacement vector at our second position squared. And that may be a lot to swallow at this point, but really all I'm saying is if you were to square both sides of this equation, what happens? You notice that the square root sign just essentially disappears, and you're left with the all of the different components squared and added together. So this is just that. These two are the same. Likewise, what's inside this bracket here is just going to be the magnitude of our displacement vector at position 1. Fantastic. Alright, well we can simplify this a lot more now. We can just write this as minus a half K, our stiffness coefficient K, times by the magnitude of R2 squared minus the magnitude of our displacement vector at point 1 squared. Alright, so this is our work done by our spring to get our ball from some arbitrary position 1 to another arbitrary position 2 while connected to a spring. Alright, and let me draw a box around that to highlight its importance. Okay, so we're almost done here. I just want to introduce one more quick thing so that we can wrap this up completely. Let's now introduce a new concept called elastic energy, and I will define, and physicists have defined elastic energy, often denoted as EE, as equaling as a half times by your stiffness coefficient times by the magnitude of your position vector at any point squared. Consequently, now we can say that our work done by our spring, so let me get this clear. This is a definition right here. This is a definition, right? So consequently, we can write our work done by our spring now. Our work done by our spring is just going to be equal to minus a half K times R2 squared plus, or actually let me factor out the minus a half K times the magnitude of your displacement vector at position 1 squared. Alright, well what's this? This will just be your elastic energy at point 2, which I'll denote as EE subscript 2. And this will be your elastic energy at position 1, which I'll denote as EE subscript 1. Consequently, now we can write our work done by our spring as just being the negative change in elastic energy. Fantastic. Alright guys, that's this video sorted. But in the next video I'm going to introduce something called conservative and non-conservative forces, and I'm also going to tell you how something called the conservation of mechanical engineering energy plays into all of this. Thanks.